Hello. This video is going to try to teach you about electromagnetic waves and light waves. So first, before I teach you about electromagnetic waves, I need to teach you a little bit about the electric and magnetic fields. Just a little bit, though. So every single point in 3D space has an electric field vector sort of on top of it. This is an example of a possible 3D vector field. So you can imagine that this is the electric field in a box. But we are normally going to pretend like the universe is two-dimensional and not three-dimensional, because it's easier to write down and visualize. Okay, so this is basically what an electric wave looks like. I stole these animations from a YouTube channel called 3 Blue 1 Brown, which is great, and you should all watch it. But it basically shows you electric field vectors oscillating up and down or side to side in a pattern, creating waves. Now, based on that previous slide, you can tell that the electric field vector at a particular point isn't permanent and set. It changes depending on if there are electric things close to that point. So it'll change directions over time, going left and right, maybe disappearing. And when electric field vectors change, something special happens. When you have an electric field that's pointing up, and then later maybe it's pointing down, that change in the electric field will create a magnetic field vector at a 90-degree angle. So you change the electric field, and a magnetic field pops up. But also, if you change a magnetic field, so for example, the magnetic field is pointing to the right, but then later you put a magnet next to it and it points to the left, that creates an electric field vector at 90 degrees. So we can get this weird feedback thing, where if you change the electric field at a point, that creates a magnetic field. And then when you change that magnetic field, that creates an electric field around it. But then, you created an electric field, that's going to create a magnetic field. And that goes on basically forever. So you get this feedback, this electric field creating a magnetic field, which creates an electric field, and it sort of spreads out in all directions. This process can be kind of complicated, but we're not going to make you do any of this math, so don't worry about it. Basically, you create a pattern of electric fields changing and magnetic fields changing, and we call this particular pattern that spreads out an electromagnetic wave, because if you look at this picture, it kind of is a wave. The vectors point up and down, left and right. So they're these transverse electromagnetic waves that are normally called light, like the light that comes out of a light bulb. It's made of this stuff. These waves have a lot of the same properties as normal mechanical waves, like wavelength, frequency, and velocity, so we can use a lot of the same math to describe them. Electromagnetic waves are really special, however, because they don't move through the water or the air. They move through the electromagnetic field itself, which isn't any sort of matter. It's not physical. So light waves don't actually need any matter to move through. They can go through outer space. They can go through thin air, basically nothing at all. And this is the cause of one of the most important properties of light, namely that the speed of light, how fast it goes, is constant. Light always goes at the same speed unless it's being interfered with by matter, like it's going through glass or water or something. It's always going to travel at 3 times 10 to the 8th meters per second in a vacuum. And in a vacuum just means when it's not touching anything. Technically, it's just rounded to 3, but it's close enough that we're not going to lose any detail by just assuming it's 3 times 10 to the 8th. That's not very easy to picture. That's this 3 with 8 zeros, meters per second, which is 300 million meters per second, which is 670 million miles per hour. That's how fast light goes. The important thing, though, is that the speed of light is constant. Let me show you one implication of this. This is a formula we learned to relate the wavelength and frequency of waves to the speed of that wave. And for normal non-electromagnetic waves, like through a string or through the ocean, you need 2 of these to figure out the third one, because all 3 of these could be variables, right? But for light waves, the speed is constant. It's always 3 times 10 to the 8th, 300 million meters per second. And this means that if you know the wavelength of an electromagnetic wave, there's only one possible value that its frequency could have. So the wavelength and the frequency, they're going to control each other. Let me do a quick comparison to show you what exactly I mean. So I'll start with normal non-electromagnetic waves. Let's say you have a wave. It has a wavelength of 3. What's the frequency? Well, the wavelength is 3. And the speed and the frequency are both variables. So you're going to get this, x equals 3 times y. It's an equation with 2 variables in it, and it actually doesn't have an answer. There's a lot of possibilities. For example, if x is 3, y could be 1. If x is 6, y could be 2, etc., etc. So this is not a solvable problem for normal waves. Knowing the wavelength does not tell you the frequency. But if I do the same problem with light waves, then instead of having a mechanical non-electromagnetic wave, I have a light wave, and the wavelength is 3. Well, the speed is always a constant. It's 300 million. So the frequency is the variable, and I just isolate the variable by dividing by 3, and I get one single answer for the frequency, 1 times 10 to the 8th, or 100 million. So electromagnetic waves are special, because for electromagnetic waves, the frequency and the wavelength, they control each other. If you know one, you know the other one for sure. The specific relationship between them is, well, let me show you. Speed is wavelength times frequency, and the speed is a constant. So this is the mathematical form, I guess, for the relationship between wavelength and frequency. And if you don't remember, it's okay. This is the mathematical form for an inverse relationship. And what that means is that if the wavelength is big, the frequency is small. And if the wavelength is small, frequency is big. So they move in opposite directions. They're inversely related. So if you have a high wavelength, you have a low frequency, and vice versa. You can sort of see that on this picture right here. On the left side, you have long wavelengths, big waves, but low frequencies. The waves aren't happening very often. And also, if you have a very low frequency wave, it's not going to be very energetic. It's going to be low energy. But on the right, I have small wavelengths. The waves are small, but they happen very often, so that's high frequency. And they also have really high energy. So this is going to be the kind of stuff that'll fry you, turn you into a skeleton. We give these different frequency ranges different names, like radio waves, visible rays, X-rays. So I'm going to give you all the names for the electromagnetic spectrum, starting with big, low energy waves and ending with small, high energy waves. The lowest energy waves are going to be called radio waves. Then we have microwaves, infrared, visible light. These are all the colors. This is everything you can see right here. Ultraviolet rays, X-rays, and gamma rays. This is the spectrum of electromagnetic radiation, starting with the biggest low energy waves and ending with the smallest high energy waves. You can remember this order if you have to memorize it using the mnemonic device. Red Martians invaded Venus using X-ray guns. That's what I used in high school. And I created a helpful little graphic for you to remember that. These are some red Martians using their X-ray guns to invade Venus. You know that they're red Martians because they're red and they have the antennas. They're X-ray guns because they're going pew pew. They're not going bang bang. And Venus is being invaded because look, oh no, it's being invaded. So anyway, red Martians invaded Venus using X-ray guns. Radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma. That's the order from low energy to high energy rays. We're going to be talking more about that later, but I hope that was helpful.